Good afternoon. Welcome to the AI Center seminar today, and it's my pleasure to introduce Antonio Stanziola. He did his PhD at Imperial on advanced beamforming for high frame rate ultrasound vascular imaging, and he joined us in the Biomedical Ultrasound group at UCL just about a year ago, I think.
Yeah, no,
and he is on a project on acoustic neurostimulation, and he's been doing a lot of interesting work on applying machine learning methods for forward modeling and acoustic propagation, signal processing, and inverse problems. So I'll turn over to you, please.
Thank you very much, Simon. So thank you, everybody, for joining and having me here. So I'm Antonio Stanziola, and I'm part of the Biomedical Ultrasound group at UCL. And as Simon said, I'm going to talk about our last project on basically building a Helmholtz equation, an acoustic solver using unsupervised learning and the application of such solver to transcranial ultrasound. And this is a work that we've been doing together between me, Simon, Ben, and Brett. So I'm just going to give a brief introduction about why we want to do this and what's transcranial ultrasound and what kind of challenges we are facing. So the key idea of transcranial ultrasound is that we can use acoustic energy to induce some form of biological effect on the brain tissue. And the kind of effect that you may want to achieve there can vary. You can have, for example, you may want to heat up a piece of tissue such that you perform ablation, so this kind of non-invasive surgery on the brain. There are groups that are working on brain-blood barrier opening. And what we're interested in is actually neuromodulation, which is the idea that you can use the mechanically, how it works is not entirely known, but the idea is that you can use the mechanical energy of an ultrasound wave to modulate the neural the activation of the certain regions of the brain, basically. And you can use it to study the brain or to perform some different tasks. And what all those methods have in common is that we need to be able to focus our ultrasound wave on a specific spot. And this requires some form of computational modeling to predict how the wave field is going to look like in the brain. And this will normally be pretty much a geometric problem if we are dealing with soft tissue. But when we're looking at transcranial ultrasound, the skull actually makes things much more complicated. So in terms of, from an acoustic point of view, it really acts like a brick wall because it's got a huge contrast, therefore reflects a lot of wave, it aberrates things, and therefore we actually need to run a proper acoustic simulation to understand how the ultrasound field is going to look like. And we cannot do this in advance in general because there is a large intersubject variability on the skull shapes and geometry and so on. And therefore, we basically have a pipeline just for treatment planning that we use to understand how to transmit such an ultrasound wave. And so basically treatment planning works like this. We start from some form of clinical data, or anatomical data. That would be an MRI, for example, or a CT. And then using some methods, we derive some acoustic property, a model of the acoustic property of the head for the subject we're interested in. And we use such model together with a provisional temporary treatment planning to basically simulate using computational modeling how the ultrasound field is going to look like in the brain. And then we keep iterating those simulations over and over, and we check each time what are the performance of the simulator, and until we get the required accuracy. So until, for example, we focus at the right place, or we should not to put too much acoustic energy somewhere else. And the work that I'm going to talk about today basically deals with this simulation part. And the reason why we want to use simulation, why we want to use deep learning for simulation can vary. And I'll start by giving an idea of what are the equations that we are trying to solve. So because such neurostimulation session require us to send an ultrasound wave that lasts quite long and has pretty much monochromatic frequency, we can model the wave propagation as a PDE, and more precisely we use the Helmholtz equation, which is again the monochromatic form of the wave equation that looks like the first equation up here. By the way, I forgot to say, if anybody has got questions, please feel free to interrupt me at any moment and ask. So this will be the shape, the form of the equation that we are trying to solve, that we are trying to simulate. And of course, such an equation is subject to some boundary condition. In this case, the boundary condition would be the Sommerfeld radiation condition that ensures that we pretty much only have upwards traveling waves. And solving such a PDE is challenging for several reasons. First of all, we have to choose discretization for our operators, and I'm going to talk a little bit more in detail about this later on. But most importantly, we have this large 3D matrix, which is a model of the acoustic property of the head, in this case, the sound speed, and for the range of frequencies and the size of the problem that we are dealing with, such matrix can be as much as 0.5 gigabyte in thought precision. So it is really a big problem that we are trying to solve. And lastly, we also have to take into account the Sommerfeld radiation condition. This is pretty much a technicality, but the core idea that I want you to get is that we can modify the original Helmholtz equation. More importantly, we modify the Laplacian by adding an absorption layer all around the boundaries of our domain. And this allows us to basically kind of get rid of this condition and solve a single PDE. And such a single PDE is very interesting because this operator here, this kind of like modified Laplacian operator, is invertible, so it's got a unique solution, and therefore we can work on it. So how do we solve such a problem? How is it solved normally in standard numerical methods? The first thing that one needs to think about is how you discretize your domain. And by all means, the most common discretization method is finite difference, where you take your differential operator, the Laplacian in this case, and you discretize it using a stencil. So a stencil would basically be like a kernel for a convolutional layer, which has got a relatively small size, either it is 3 by 3 or 5 by 5. And the problem with such approach is that it requires, in order to approximate derivatives good enough, it requires a very fine discretization of the grid. Therefore, the computational problem gets even bigger than what I described before. So it's challenging to apply such method. Another thing that you can do is to apply pseudospectral method, where the derivatives are basically calculated in the element-wise product in the Fourier domain and then brought back in the spatial domain. And this has got us, I mean, it is faster for larger problem, but requires you to do some FFTs. And lastly, there are like methods like finite elements and the, let's say, kind of recent physics-informed neural network, where you have, so in the finite element case, you have a mesh that depends on your problem. And in the case of the physics-informed neural network, you actually have a neural network that represents your problem. And the main issue with such discretization method for what we're interested in is that they are problem dependent. So each subject is going to have its own mesh, or in the case of physics-informed neural network, each problem is going to be solved by basically optimizing a different neural network each time. And this makes it a little bit challenging to build up a method that you can apply in different problems and on different subjects. So in terms of the discretization, we use the pseudospectral method. So we're just taking our problem and we're discretizing it on a grid. And the size of the grid is pretty much given by the Nyquist limit. So it's defined by the maximum spatial frequency that you need to model. So once you get a discretization, you have to think about how to solve the problem. And from an intuitive point of view, the most straightforward way is just to take the standard wave equation, the temporal wave equation, apply a monochromatic source, and then run the simulation until you get to steady state. But most often, the way those problems are solved, being PDEs, is by having some kind of iterative method that iteratively solves the linear system associated with the PD and the discretization that we described. And the most used method, they're called like Krylov methods or Krylov subspace methods. And basically what they do is that they build up a subspace by repeatedly applying the forward operator. In this case, will be the Helmholtz operator. And after building such a subspace, they try to solve, those methods solve the problem in this subspace and then project it back to the original space. So the most famous Krylov methods would be either GMRES or conjugate gradients. But the problem with those methods is that because they repeatedly apply the forward operator, they can be slow when your forward operator is local, and that would be the case of the Laplacian. So what happens is that the solution, as we will see later on, will slowly grow from the source point outwards. And there is also a lot of other problems with the Krylov methods. So you need to have some form of preconditioning to get rid, to kind of mitigate this locality problem of the forward operator. And this is another problem of its own. How do you find a suitable preconditioning matrix? And also you may have storage problem if you run it for too long. So you need to save the matrix that allows you to project back in the original domain. And since each vector of this matrix will be half a gigabyte in our case, you cannot really, especially if you want to solve the problem on GPUs, you cannot really build a very large subspace. So because of all those considerations, what we've thought about is to basically learn a solver. So learn, in this case, a neural network that takes a PDE with different parameters, different speed of sum up, and then slowly builds up the solution. And this brings us to the problem of, to the topic of learn iterative solver. This is actually most known in the deep learning community as meta-learning, because often people try to learn a neural network that is capable of optimizing other neural networks. In this case, we're literally just trying to learn how to solve a physics problem. And we want to do it in an iterative way. So the general idea is to have a neural network or some form of parameterized function, which is the f here, parameterized by some weights theta, that takes the current estimate of the wave field, which would be UK, takes the parameter of the PD, for example, the speed of sound or the source, so C and rho, and then gives an update that we can sum to our current estimate of the wave field to get a new one. So this is, I mean, this is very similar to, for example, what people do in ResNet blocks. The problem with such a formulation is that we want to apply this on very large problems, and we have inputs of the network that belong to fairly different domains. So one would be a wave field, another one would be, for example, a speed of sound map. So the network has to come with a method to combine them together, and this adds some further complexity on the relationship that the network has to learn. So we applied a slight modification of this method. What we did is that instead of feeding the network with the current estimate of the wave field and speed of sound and source wave field, what we do is that we feed the residual, which is this A of k here. And the residual will basically be what in physics for neural network will be roughly called physics loss. And it's basically a signal that tells us how close we are to the solution. So if we are solving the wave equation exactly, this term here is going to be 0. So the residual will be 0. And A here is the forward operator, so it's the Helmholtz operator. So this is literally a linear system. And the only difference is that the forward operator depends on the speed of sound. But this is something that we can compute because we know the physics, we know how to discretize this, so we can compute this residual vector and we can feed it to the network. And the last modification that we add to this scheme is that we wanted to retain some form of memory of the previous updates. And the intuition behind this, there are several intuitions behind this idea. The first of all is that if we look at standard iterative solver, most of the time they have some form of memory. So the simplest example would be momentum for gradient descent, where you keep track of the previous update. Adam or conjugate gradient where you have the p vector, or GMRES where you have the period subspace and so on. But anyway, the core idea is that we are augmenting the inputs of the neural network with a hidden state, which we call h of k. And now the output of the neural network is going to give two different outputs. One will be the update of the wave field that we apply as we have seen before, and another would be the hidden state for the next step, basically. And it's actually, this has got a connection with some other work that is done for imaging, painting, and denoising, which comes under the name of recurrent inference machine, and they do something which is fairly similar. The main difference is that in that case, the residual vector, they don't fit the residual vector, but they actually fit the gradient of the loss function. But anyway, this will be the shape of the update that our network does. And just to make things more clear, this will be an example of unrolling such an update, so to have visual representation of what's going on. So this is our neural network, and those are the three inputs that I just described. The only thing that we've added on top is that we are also feeding this perfectly matched layer, actually the absorption coefficient of the perfectly matched layer to the neural network. And the reason why we do this is that later on I'm going to show you that this is a convolutive architecture. Therefore, we have to give some form of signal that tells the network to behave differently on the edges of the domain, because that's where the absorption happens. Otherwise, you will have reflection going inside of the field, and that's the kind of signal that this PML gives to the network. And this is, again, iteratively applied until we get to, for either a given amount of steps or until we go to convergence. So this is in terms of how the overall idea. I'm just gonna talk a little bit more in detail about the architecture. And the main thing that we wanted to do is to make a lightweight architecture. And the reason is that, again, we are aiming to apply this later on very large problem. So having a neural network with a large number of parameters may make the whole computation prohibitive, especially on GPUs. So what we did is that we make a very lightweight neural network. It's got only like 47,000 parameters. So compared to like standard deep learning model, it's very light. And it's pretty much based on the UNet. So we have double convolutional block that lifts the input. Oh, by the way, the input of the neural network will be a complex field. We just get around it by having an input with two different channels representing the real and imaginary part. So the input gets fed to the double convolutional layer, which lifts it to a different representation space. And then we have the classical hierarchical multi-scale architecture of a UNet. And actually, the multi-scale architecture makes sense for this problem because most of the advanced methods used to solve PDEs, and especially wave-like PDEs, like the Helmholtz equation, they create a preconditioning matrix, which basically is a multi-scale representation of the problem. So this makes sense from that point of view. The main modification that we made to the UNet architecture is in this encoding block here. So the encoding block is slightly more complex, but not much more complex than what the UNet has. We have a hidden state, which is the H that I described before, and this hidden state is fed with the input to the double convolution layer by simple concatenation. And then we also have this other piece here, this two concatenation and double convolution layer, which estimate the next hidden state for that block, which means that actually our hidden state is also multi-scale. So each encoded block has got its own hidden state, and of course this each one of them has got different scale due to the downsampling. And in terms of the downsampling, we don't use pooling layers, which are often used in UNet, because we don't really want to scale down the wave in a meaningful way. Therefore, what we do is that we learn a restriction operator, which is nothing more than a convolution with stripe 2 and a kernel which is 8 by 8. And the same thing happens on the decoding block, where the input from the preceding downsampled layer gets upscaled by learnable upscaling block, which is a transpose convolutional block, basically. And every single double convolution block that you see here, and then you can imagine in each one of those inner blocks has only got 8 channels. So we only have, each double convolution block has 2 convolutional layers interleaved with a nonlinear activation, which is a prelude in this case, but each one of the convolution block has always got 8 channels at each depth. So normally channels are double when you go down. In this case, we keep them constant. And this allows us to have, to basically create such lightweight neural network. So that's in terms of the architecture. Again, if anything is not clear, please ask questions. Now we go into the data set. And the data set also requires a little bit of thought. So normally what people will do is that they will run a bunch of simulation using a very high performance code that possibly takes quite long. And then for each forward problem, we actually have the ground truth. We know how the wave field is going to look like. The problem is that if we want to apply this on the 3D problem, that's going to require like weeks or months. And the reason is that solving the problem, I mean, that's the reason for doing this work in the first place. Solving the forward problem with standard methods takes long. Therefore, building a data set is going to take very long. And the other thing is that you may not be sure that the data set that you created is representative enough. So you may want to change the data set and then you go back and run another bunch of simulation that takes another 3 or 4 weeks and so on. So what we decided to do is to see if we can train the neural network using, first of all, very simple data sets, and second of all, without any ground truth. So in terms of the data set, we've made those very, very idealized skulls. Those are 96 by 96 pixel images, and they're just made by summing up a few spherical harmonic to get roundy-ish shape with some deformation. We have random thickness, and we have a contrast on the speed of sound that more or less matches the contrast that we are expecting to see in the when we are applying this method to real problems. And we also need to define the source, and we used a point source at a fixed location, which means that throughout the entire training, what the neural network does is that it sees the source always at the same place, although it doesn't see the source, it only sees the residual, but the source position is always located at the same place for the training set. And actually the training set has 9,000 examples of like those. But then we have another set of 1,000 examples. That would be the validation set that we check every 10 epochs while we are training. And in case of the validation set, the source position is actually randomly located around the skull. And the idea is that in this way, the validation testing on a validation set with a slightly different problem gives us some information about the generalization capability of the network. Can it generalize to sources that are located in different positions? And because of this, one thing that we do, which is actually very important to be able to get a good performing model out of this training, is that, as I said, every 10 epochs we check how the neural network behaves on the validation set, and more importantly, we check how it behaves after, I don't know, like 1,000 iterations, and we save the neural network that has the lowest loss at the validation set. And this is very important because otherwise, during training, you may overfit on the training set, and therefore you get a solver that only works for those basically very simple skulls. So again, as I've said before, we don't have any ground truth. We don't run the forward simulation on a solver before, so we don't know what wave field to expect. But what we know is that the residual has to go to 0. So in parallel to what is done in the vast majority of iterative solvers, we try to minimize the magnitude of the residual. And how do we do that? Well, as I said, this is an iterative method, so we keep trying to update the solution. Therefore, the loss that we use is the average loss across all the iteration. And again, this may not be the optimal thing to do, but it gives us some information about, I mean, it allows us to backpropagate losses at every step of the solver. So if we were, for example, solving using as loss only the very last iteration, then we may have a solver that behaves very badly for the first, I don't know, 100 or 200 iterations, and then it converges to the solution fast. But actually, we want to have a solver that even at the first, at the very beginning of the iterative optimization gives a decent solution. So that's why we use this average across all time steps. But again, this is a kind of a hand-wavy explanation, but that's the idea behind it. And lastly, this t here, which will be the terminal iteration, this is set to 1,000. And as you may imagine, although the neural network is very lightweight, backpropagating through 1,000 iterations is simply unfeasible. So what we did is that we use a replay buffer, and then we use truncated backpropagation through time by backpropagating only from 10 steps. So what the replay buffer does is that it stores triplets of inputs to the neural network, which will be the wave field, the residual for computational reason, and the hidden state. And then when we're training, we randomly sample, let's say, experiences from this replay buffer, and each one of them is going to start at a specific iteration. So let's just like visualize it as this line here, and then we run the neural network for 10 iteration, perform backpropagation, and then take the sample and put it back in the replay buffer. And then we keep doing this over and over. We actually train it on 6 GPUs using distributed training. So we have 6 copies of the neural network, each one with its own replay buffer. And then by the time one of the sample of the replay buffer reaches the final iteration, then what we do is that we just replace it with a new speed of sound map that's starting from the time step 0, and we keep going over and over. So this is basically the results on the test set. So there is another 1,000 example of those idealized columns which we test after training. And as a reference, we used a time domain solver. We actually use K-Wave, which has been developed in our group. And the idea is that by using a solver that is solving a different equation, the wave equation, we are actually checking whether our solver has learned the physics. And it actually does. So if we compare the reference wave field coming out of K-Wave for this specific speed of sound and the prediction, we see that the difference after 1,000 iterations is well below 1%. So from the point of view of the physics, we have kind of learned to solve the problem on the test set. And interestingly, the L infinity error, which will be the ratio between the maximum error in our wave field prediction and the biggest value of the wave field, gets below 10%, sometimes even after like 50, 60 iterations. Sometimes it takes longer. It depends. Actually, it turns out it depends on the geometry of the speed of sound map. But in general, we can safely say that at least on the test set, after a few hundred iterations, we are able to solve the problem with an arbitrary speed of sound map. So this is as much as it goes for the for checking that the solver works. But then what we did is that we compared it with the GMRES, and this is a very standard GMRES. There's no preconditioning going on. It's an off-the-shelf. It's actually MATLAB's GMRES. And we can see two things here. First of all, is that we get to the solution much faster than vanilla GMRES in terms of like the L infinity error. And actually, so the dotted line represents here the average, and the solid line represents the median. And in terms of median, we get below 1% of error after about 100 iterations. On average, after 200 iterations, but anyway, it goes down pretty fast. And another thing that we can see here is that we can basically here I'm correlating the magnitude of the residual, which is the loss that we're actually minimizing, with the L infinity error, and we see that of course they are pretty much correlated. So this means that when we're applying this method we can use the residual magnitude as a proxy to know how close we are to the true solution, and more or less in the sense that if we go, as you can see in this plot, if we go below roughly 5 times 10 to the minus 5 in terms of residual magnitude, we are pretty sure that the L infinity error is below 1%. In between, there is actually quite a large spread, but at least we have more or less a threshold. And So if we look at the distribution of the error at the final iteration, which will be 1000, we get something like this. And here the RMSE error is more or less like the magnitude of the residual compared to the magnitude of the field. And again, compared to GMRES, we can see that the results are pretty much very clustered around very low values. So almost all the examples in this test set have a very low L infinity error. There are a few outliers that I'm going to briefly mention later on. And the same thing happens for the RMSE. Just to give an insight on why this is working better than GMRES, for example, what you can see, so here I'm plotting the wave fields at different iteration number, and GMRES on top and the learn optimizer on the bottom. And what you can see on top is what I've been describing before, the fact that in GMRES, at least without preconditioning, the updates are very local, so the solution is slowly growing from the source position outwards. While for our learn optimizer, actually already after 10 iteration, it has spread the estimate of the solution pretty much everywhere, and after 100 iteration, we are more or less converged to the right solution. So there are minor changes going on, but we're pretty much done, which is actually very important for our application because you may want to have a rough estimate quickly of the wave field. And so this will be an example that tries to show what is going on inside the neural network as it's solving a problem. So this is, on the left side, is our current estimate of the wave field. This is the residual that is fed to the neural network via applying the forward operator to the current estimate. This is the update predicted by the neural network, and on the bottom here, I'm showing what the hidden states are doing at each time. One thing that I haven't mentioned, the hidden state is actually, it's kind of represented as a complex vector in the sense that has got two channels and size given by the scale depth at which it's located. And what you can see here is that although the residual is pretty much focused around the source point, the neural network was able to actually spread it around and has already understood that the wave field is going to go around on the side, but it hasn't really spread it on top because it doesn't know what's going on here yet. So it is actually doing something quite interesting. Another question will be what the hidden states represent, and this is actually beyond my understanding at the moment, but I think it's still interesting to see what's going on. So if we look at this image as the optimization progresses, we get something that looks like this. And as you may see, it looks like the states have learned some form of meaningful representation of the optimization process. However, again, I'm not entirely sure what they mean. But we can see if we look at the wave field estimate here, we can again see that it converges fairly fast. So yeah, so that's as much as we can understand of what's going on in the neural network. And if we want to look at that step by step, we see similar things. After a single iteration, the wave field is already spreading inside, and after 10 iteration, the network has already figured out more or less. So there are some reflection going on here. The hidden state are keeping track of the location where the source wave field hits the skull. And by the time we get to 50 iteration, we're more or less done. So that was as much as it goes for the test set. But then again, we would like to apply this on very different problems and on very large problems. So we start to ask ourselves what happened, how well this network generalizes. And we're basically tested out by applying different conditions to the problem. So the very first test that we did, it was on a very simple homogeneous rectangle. Again, the network has never seen a shape like this. And this is to understand if the network has more or less learned some priors on the possible wave field, or has learned some physics prior that help it solve the problem generally. And again, as we can see here, we get a very good prediction. The error is still well below 1%, but interestingly, it is as fast as it is on the test set case to solve the problem. So as we've seen before, there are quite a lot of examples where the solution is achieved between 100 iteration, and that's what actually happened in this case as well. And just to be sure that this doesn't only happen with very geometric, to be sure that the network is not only able to solve simple geometric speed of sound problems, we also tried with the speed of sound map that is actually a picture of Helmholtz. And again, we get a very good agreement with respect to the reference simulator. So we can more or less safely say that at least within the range of speed of sounds seen during training, the network is able to solve the problem, is able to do it very fast. And then the second question is, now how are we going to train this network for solving very large problems? And again, we want to try to see whether we can do patch training, which means can we train on very small example and then expect it to generalize on much larger domain? We know that the convolutional architecture can work on arbitrarily sized inputs as long as all the downsampling operation makes sense. So what we did is that we stuck together 24 different examples from the test set, and we try to predict the wave field here. And here, again, the domain is about 490 by 490 pixels. And I just want to remind you that the network has been trained on a 96 by 96 speed of sound maps. And what we see here is that, of course, it takes longer to get to a decent solution, to get below 1% of error. But nevertheless, the network is able to do so. So it is able to generalize on larger speed of sound distribution with sources on slightly different location. So this made us very confident on the fact that the neural network was actually doing something interesting. So the next step was to actually apply it on a fairly realistic problem, as much as a 2D problem can be realistic. So we took a real city map from a dataset which is available online, and made this sound speed map of 512 by 512. Again, here all the contrast makes sense. All the contrasts are the same that we will have on a real application of this technique. And we also changed the source map. So far we've always seen point sources. Here we actually have an array, so an arc of point sources that allows us to make a focused field. And again, also in terms of the field, the network has never seen a focused field during training. The field was always generated by a point source, so it is very unlikely that it gets focused unless you have a lens or something around. And again, even in this example, which is everything super different compared to what we've seen in training, the network is still actually able to reconstruct the field within 1% of error. Now it takes even longer than before, but then that makes sense because the wave field is very complex. There is a lot of modes in here, many reflections, and so on. But we still get below 1% of error. It takes about 2,500 iterations, but we can get there. But more importantly, the focus is reconstructed in just 200 iterations. And that makes us confident on the fact that this tool can be used in real time. And this is actually the example that I'm showing here. So this is the solution that the neural network gives at each iteration. And as you may have seen at the beginning, the focus is reconstructed in a small number of iterations. It takes about 200 iterations. But then we can keep updating the solution by moving the transducer, the array of sources on different locations, and that will mimic what a clinician could do in a neurostimulation session when he wants to try for a given patient what kind of wave field you get by placing the transducer on different locations. So this whole video is it's actually computed in about 12 seconds. So the whole network has been written in PyTorch, so we are fairly confident that with by writing the network on a lower level programming language and optimizing everything, we can definitely get this thing working in real time. And that's as much as the results go. I just want to briefly mention a couple of things about those outliers that we've seen in the results. So there are some situations in which the neural network actually gets it very wrong. So we can get error up to 10% of the true wave field. Actually, if you look at the wave field itself, they're not super different. So the bulk of the wave field has been reconstructed, but actually there are some structure, some kind of model structure that are not that are not well predicted by the network, and sometimes you even get the network to diverge. But interestingly, the example for which the network, let's say, fails, they're like very well geometrically defined example, like this one, where the speed of sum up is pretty much like a circle. And interestingly, also time domain solver take much longer to reach state in those cases. So there's possibly a physical reason behind why those problems are complex. And interestingly, also, this doesn't really seem to happen with much more complex speed of sound distribution, like in the real skull that I've shown before. So to conclude, what we proposed here is a very lightweight neural network. It's 47,000 parameter, and it has learned to solve the Helmholtz equation basically from end to end. So there is no ground truth here, that we're just using a physics loss, and it works with the heterogeneous example. We can change the speed of some map, and the network still has pretty much the same performance. And again, it seems that it generalized very well outside the training set. So this is basically the conclusion. Then of course there is still some open question, like what would be the best training strategy? What kind of example do we need to show to the neural network to expect it to work well on all the possible cases that we will see in a real application, or whether we can actually remove the plate buffer? How can we be sure that the network converges? What would be a good loss function? Or we have just used the average of the magnitude of the residual, but there might be like different loss functions. And yeah, so this basically concludes my presentation. I hope everything was clear, and I'm very happy